Thanks everyone for being here today. Catherine, this is a special lecture, which I think most of you know since it's at a special time. But our lecture is the Katherine and Arthur Sehlin lecture today. And it's got a proud decades-long tradition of honoring the values of Mr. and Mrs. Sehlin. They were both engaged in many volunteer and professional activities during their lives and exemplified leadership, personal commitment, and a sense of service throughout their entire lives. Katherine Sehlin was noted for her activities in the area of social service and was joined by Arthur, who worked together with her to advance many human service causes. Arthur Sehlin enjoyed a long, successful career in civil engineering, which is why we're the recipient of this lecture every other year. And both were deeply committed to higher education, and their pride in the University of Minnesota inspired the family to create this lecture series that we're enjoying today. The lecture series alternates between our department, the Department of Civil, Environmental, and Geoengineering, and the University's School of Social Work. So please join me in a round of applause for the Sehlin family, some of whom we have here today. And others are joining us on Zoom, and thank them for their generous support of this lecture series, which allows us to bring in excellent leaders like Patrick, who will be speaking to us today. And I'd also like to give a quick applause to Shirley, whose birthday was last Friday. So, happy birthday. And I'm also really grateful that we have the philanthropic support of the J.S. Braun Intertec Visiting Professorship, which has enabled us to bring in Dr. Patrick Ray. So we have Sean Schwartz in the back, who's from Braun. And this visiting professorship was created more than 30 years ago by our CEGE alumnus, Mr. J.S. Braun, and the company that he founded, Braun Intertec. And this allows our college to attract outstanding visiting professors. Patrick will be with us for about 2 months this year, working with faculty at the St. Anthony Falls Lab and kind of helping to expand our capacity and encourage new collaborations, which we're really excited about. And we also have another visiting professor, Michael Marsalek, who's not here with us today, but he's also visiting as part of the Braun professorship. And the goals of this visiting professorship are to advance collaborative education, research, and policy with us at the university, and also with the professional community related to construction materials and pavements, as well as geotechnical, hydrogeological, transportation systems, structural, and environmental engineering. So it covers a wide range of areas that we can bring people in and collaborate with. So please join me in giving Sean a round of applause. And so now for our speaker, Patrick Ray, our J.S. Braun visiting, our Intertech visiting professors, is an associate professor of environmental engineering at the University of Cincinnati.
Just got promoted. I love hearing associate. That's really fun.
He's a specialist in the development and application of numerical models of the integrated human hydrologic system for risk management under the uncertainty of change, including climate change. He's the lead author of the World Bank's 2015 Decision Tree for Confronting Climate Uncertainty in Water Resources Planning and Project Design document, and is also a primary scientific contributor to the International Hydropower Association's 2019 Climate Resilience Guide. He's also a primary scientific contributor to the California Department of Water Resources 2019 Climate Change Vulnerability Assessment and UNESCO's 2018 Collaborative Risk Informed Decision Analysis. And so he's done a lot of work in this really interesting intersectional area between environmental change, climate change, and decision analysis, and how do we make better decisions in the context of all of this change that's happening right now. In 2022, he served as a climate resilience lead for the United Nations Economic Commission for Africa. So Patrick, we're absolutely thrilled to have you here, and the floor is yours.
Thank you. All right. This is a tricky time of day, tricky time of week to give a talk. I'm sure you all are worn out. I'm sure you're ready for Friday evening. So I'm going to roll up my sleeves and try to be as fun and interesting and entertaining as possible. So we are, just so I make sure I understand the timeline, we're done at 4:30, and then we move on. Okay, got it. All right, well, I will aim for about 45 minutes and hopefully have plenty of time for questions. Where's my stopwatch? Okay. All right, and I'm going to try some technology. Here we go. This is a photo taken by one of my grad students, Asphota Wasti. She's from Nepal. So there's a pretty river in Nepal for you to enjoy. All right, it's very important to me that this lecture is accessible. I don't even like the word lecture, but it's a lecture, I guess. That it's accessible, that it's interesting, that it's inspiring, that it's inviting, that you feel by the end of it like you're more equipped to do your job, like you have bigger ideas for how you can apply these kinds of notions, these kinds of paradigms to the type of work you do. So I'm going to emphasize stories. Hopefully that will go well. That will be more memorable than analytical results. I'll start with the motivation. The motivation is, here we go. Whoops, that was the wrong button. Okay. Okay. Do we need more water infrastructure in the first place? Haven't we already built all the water infrastructure that we need? What's the point of building more water infrastructure? It's expensive, it's risky, it comes with all kinds of negative side effects. Why would we be motivated to build more water infrastructure? And if we are going to build more water infrastructure, why not just build for the expected conditions? Why not look at the past and see what types of climate conditions we've had in the past and then just build it for that? Or we know climate change is happening, project for climate change, say, oh, climate change means 2 degrees of warming. I understand that. I'm going to design for that. Just build for that, right? We don't do that. So why not do either of those things? I'm going to talk about decision science, which is the world I live in. This is, it is civil and environmental engineering, but my specialty is decision science inside of that, which is something that I think a lot of departments don't emphasize. The value of our infrastructure is what motivates us to build it, and it helps us quantify the benefits and costs of whatever particular investment inside a portfolio of investments. And the big picture is a sort of a vision for the types of things that I think are most necessary for our research going forward in the next 10 years or so. I'll use the story of the Ohio River to talk about the value of infrastructure and a story of South Africa at the end that will turn into a story of Minnesota. Okay, the motivation is decision-making under deep uncertainty. Let's start with climate change. There's all kinds of uncertainties, and I'll be talking about uncertainties more broadly as we go through, but let's start with the uncertainty of climate change, which sort of started my journey through this field. Here's a picture of climate change in the last 100 years. It's red, right? It's not blue. Red means warmer. So it's gotten a bit warmer, and it's not uncertain. This is climate change increasing since about 1970 or so, very clearly, very distinctly, without a lot of controversy. Politicians don't argue about this. We don't have debates about whether there is climate change or not. This is just what's happening in the world. If we were to design for this, it wouldn't be that hard. We would just say, oh, well, temperature's going up like this, so we're going to accommodate that into our designs. No big deal. It's not a very challenging problem. This, however, is a challenging problem. This is a deep uncertainty. Does anybody recognize this image from the Intergovernmental Panel on Climate Change? Yeah? Okay, so here is what the Intergovernmental Panel on Climate Change is telling us. This is a group of climate scientists from all over the world. It's really a collaboration. It's really a sort of community of scientists that are loosely held together by the sharing of certain scenarios. Here is a scenario that they all think about together. And this scenario is a lot of carbon emissions, a lot of methane, a lot of development on planet Earth. And this is another scenario. The blue scenario is less of that. Less carbon dioxide emissions, less methane, less development. And what they do is they take these scenarios called forcings. The old version was called the representative concentration pathways, or these forcings of the atmosphere, and they run them through all of their climate models. The climate models in this case are called general circulation models, and they're these huge models with big chunks, 2.5 degrees latitude, longitude, all over the world. And those general circulation models give the output of what the climate would do if it were forced with all sorts of different amounts of greenhouse gases. What we're looking at here on the y-axis is just the temperature. What we're saying here is if you have this kind of forcing, we think the temperature might be somewhere between 3 and 5 degrees warmer by the end of the century. And if you have this kind of forcing, the temperature might be 0.5 to 1.5 degrees warmer by the end of the century. The difference between those things is what we call irreducible uncertainty. The fatness of these, fatness, that's not a nice word, is it? The thickness, what's a nice way to say that? The width, there you go. The width of these lines is the scientific uncertainty. That says, if we do our climate science better, then we can make this a little bit narrower. We could shrink this line a little bit down here, because what we would do is we would improve our climate models such that if you put this scenario of greenhouse gas forcings into your climate models, you would get a more confident result, and that would shrink down a little bit. Same thing up there. That's the scientific uncertainty, which in theory we could improve if we did more experiments and made better models and better understood climate dynamics. The difference between the blue and the red is Vladimir Putin and Donald Trump and MBS from Saudi Arabia and Elon Musk and what the heck is going to happen on planet Earth over the next 20 to 50 years. It's, are we all driving electric cars and using solar powered solar panels on our roofs, or are we burning a lot of coal and having a highly integrated planet where we ship everything around? That's crystal ball stuff, and we can't do anything. There's no experiment we can run to know that better. What this means is that we have to accommodate this into our engineering designs. This is the context for the future in which our infrastructure will live. If we build it around here, 2020, it may live in this future and it may live in this future, and there's no way to know. So we have to somehow accommodate both of those possible realities in our designs. Okay, so far I've only been talking about temperature. And there's a wide range of what temperature could do to our experience of planet Earth. But what is the effect of that temperature change on the hydrologic cycle? This is the stuff that we are interested in. When you increase the heat, when you add heat to the hydrologic cycle, you speed it up. You get shorter rainy seasons, more intense precipitation when it occurs, longer periods of drought in between those bursts of precipitation. You melt your storage, which is a profound problem. Much of our storage historically has been in snow. We're losing that. And you also evaporate more of your reservoirs. The increased evaporation and transpiration results in a general drying out of the ground. So there's your sort of precipitation-based impacts. You go from global warming, temperature increase, to changes to the hydrologic cycle, to all of these other cascading uncertainties. We don't quite know what the temperature is going to be in the future. We don't really know with huge confidence what impact that range of temperature change will have on the precipitation. And then we go into, well, what happens to agriculture? What happens to the energy sector? What happens to hydropower and cooling for your power plants and everything else? The uncertainties cascade. So this is our deep uncertainty probabilistic design problem. Like later on, I'm going to say something about calculus, but I'll throw it in right now. Statistics is so important, and these poor students take so much calculus. They take calculus after calculus. They take like 17 calculuses before they get to my class when they're seniors at the University of Cincinnati, when it's the first time they're really seeing statistics. And my little heart breaks. I really believe in the need to infuse and inspire these young people with probabilistic thinking and statistical tools much earlier because of the size of these uncertainties they deal with. Okay, so we've got these problems. We've got maybe a lot more temperature, maybe not a lot more temperature. We've got effects on the hydrologic cycle that are floods and droughts, and that cascades into all kinds of other things. But this is not a big deal, right? Floods and droughts, I'm not scared. We've been dealing with this for thousands of years. The Romans, the Persians, the Chinese, the Incas, everybody has dealt with this problem for thousands of years by just building dams. No big deal. We've always built dams. Well, okay, so the World Commission on Dams about 20 years ago, published I think in 1999, begins to question seriously whether continuing to build dams in the modern world is a good idea. It was such a compelling verdict, maybe, on large dams in the world, concluding that the costs of these large dams outweigh the benefits. The large dams built all over the world do more harm than they do good. They don't justify themselves. So it was so compelling that the World Bank, for example, in about the year 2000, stopped building dams, stopped investing in dams. It's like a huge thing that they do. Just didn't build any dams from about 2000 to 2008. Something interesting happened around 2008, and they started building dams again. But it's worth rigorously and seriously asking the question, can we solve the problems, the hydrologic water resources problems that climate change poses in the same old way that we've always done it, with dams? I'm not going to answer that question for you. I'm just going to challenge you that this is the type of stuff I analyze, and this is the type of stuff that I love thinking about in America, in other countries. Okay, all kinds of risks, all kinds of challenges, all kinds of terrible pitfalls and depressing ideas about this terrible future that we're hurtling toward. My whole life is risk assessment, right? The title of this talk is risk assessment. That's my son up there. Can you see that? Oops, sorry. This is my, oops, one more. That's my kid up there. His name is Marcus. I was coming home on my bicycle, the University of Massachusetts. He was probably, I don't know what, 6 or 7 years old. I'm on my bicycle and my head's down and I hear singing from the top of the tree. I didn't see him up there, but he's reading a book. He's sitting at the top of that tree, singing out loud, reading a book. He's not interested in risk assessment as like risk management, I should say, as a life mission. He wants to live and he wants to be bold and do wonderful things in the world. And he wants to dream that the world can actually get better. And it's not just getting worse all the time. Here's the other kid at about the same time. This is Sammy. And Sammy is just unafraid. He's afraid of nothing. So if we start talking about all the risks of climate change, he's just going to start fighting. He's going to start ninja chopping. These kids are my inspiration, but also that's sort of weird if they're my inspiration. I want to be their inspiration. I want to help them learn and help them believe that those who are caring for them, like me and like all of you who are an inspiration to me, are working on a world more wonderful, more beautiful, not just marginally less terrifying for them. So that's my approach to these sort of water resources challenges. Not fearful, not timid, but taking a hard look at what the challenges are, quantifying them, measure them, and making good decisions in the belief that we can actually figure out these challenges. Okay, so here we come to decision science, which is sort of how we do that. How are we going to look in the face of these deep challenges that we are being presented by a rapidly changing world, changing in all kinds of ways, climate change and everything else, and work our way through to better decisions? So we're talking about serious decisions to make. We want to help institutions like the World Bank, like the US Army Corps of Engineers, like UN, the UNESCO, whoever it is, California Department of Water Resources. We want to help these institutions that have very serious decisions to make, meaning people are relying on them getting it right. They can't just blow it. So how do we give them the tools that they need to do vulnerability assessments and stress tests on the types of designs that they're considering? Here's a story. This is an extra bonus story. I didn't write the story down. Here's an example. I'll call it an example, not a story. Here is Malawi. Here's a World Bank project in Malawi. Lake Malawi here, the Shire River. Here's precipitation on the y-axis and temperature on the x-axis. And let's say that the long-term historical conditions in this river basin, are about 1,000 millimeters of precipitation and about 20 degrees Celsius. This is just their long-term average conditions. Maybe from the middle of last century, it's gotten a little bit drier and a little bit warmer, right? So this is the middle of last century and the end of last century. But okay, we can design for that. We can say, I understand these conditions. I know how to design a hydropower project, in this case, for those conditions. Well, climate change, right? Now we get those Intergovernmental Panel on Climate Change projections for this region, and they look something like this. A huge mess of maybe, let's call them about 100 or so projections. It's about 25 different laboratories throughout the world where they're making these projections, and then they make them over multiple scenarios at each laboratory. And you end up with something like this. Well, maybe you're terrified and you say, well, forget that. I'm not going to look at that. That's a mess. Half of them are wetter, half of them are drier. What am I going to do? La, 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 la. I'm not going to do anything. I'm going to go back to this. Whoops. I'm going to go back to this. If you say, well, forget that. I'm paralyzed. I don't know how to accommodate climate change. I'm just going to build for the historical conditions. Then you may end up with something called regret, right? We may have something called regret, where let's say you built for the historical conditions, and if any of these things were actually correct, these climate change projections, if these were correct, then you're going to really wish that you built a smaller hydropower project because it's drier than you designed for. And if any of these projections are correct, then you're going to have regret in another way. You're going to wish that you had built a bigger hydropower project because you could get all this rain up here, all this water rushing through past your turbines that you can't accommodate because you designed for too small a hydropower facility. So what can we do with that sort of daunting uncertainty? How do we move forward? How do we not get paralyzed by that kind of uncertainty? How do we design for a spread? Well, one way to do it is to invert the question. So this is a significant moment in my life when I began to understand this. When I was a postdoc, my postdoc mentor, who's so wonderful, he helped me to see this, this inversion. We're not going to ask the question, what performance do we think we're going to get under these conditions? We care a little bit less about what performance I'm going to get here. That's a condition. Could possibly happen in the future. That's a precipitation and temperature. That's a precipitation and temperature. That's a precipitation and temperature. We're not going to get worried about what performance we might get at each one of those dots. Instead, we're just going to say, well, I don't care about all those dots. I just need to know the conditions under which my design will fail. I'm going to do a vulnerability assessment. So here's how we do that. We start with a climate model. We call these cute little things weather generators, which makes it sound as if we're super powerful people that can make the weather. We just model the weather. We don't actually generate it. This is really terrible, but we like saying that we can generate the weather. So we start with a climate model, and we run that through, and this is just what's happening in the sky, right? This is how much is it raining? What's the wind doing? And then we bring that water down onto the ground in a hydrologic model. And this tells us what the water is doing in the river, how much water is going into the ground. And then we put it into something called an impact model, which is like an infrastructure model or a hydropower production model, something like that, a groundwater yield model. When you set up this little workflow of models, you can loop back around and you can run thousands of scenarios this way pretty quick. So we make a bunch of scenarios, maybe thousands of scenarios, and this is Massachusetts, yeah? So we're running lots and lots and lots of example conditions through our model workflow, right? And what we end up with is that change in precipitation and change in temperature, but we don't care about all those. Well, that stupid thing has dots. It's dumb. Okay, lots of dots all over here. I got to change this slide next time. It shouldn't be dots, right? It should be just blue. Okay, but here I am saying there's no dots, and you're like, there's thousands of dots. Okay, here's the blue area, and here's the red area. What we're saying is, forget what the GCMs are telling you might happen. Forget climate change projections. It doesn't matter. Just tell me the conditions under which your system breaks, boom, area of hazard, if you have precipitation and temperature combinations in here, your system breaks. And if you have precipitation and temperature combinations in here, your system's fine. That's all I need to know. I don't need to know what the future holds. I just need to know that I'm fine as long as I'm not up here in this region of climate change. So I don't actually need to know what the climate change is. I just get a sense for the amount of vulnerability I have. And then the last thing you do is put the likelihoods on there. And this is that cloud. So picture the cloud of GCM dots from the previous slide. Put that cloud on here. And if you see that almost the whole cloud is in the blue zone, and only a tiny little bit, maybe a couple projections out of the 100, maybe 1 or 2 of the projections are in the red zone, you might say, well, it doesn't look to me like I'm carrying a ton of climate risk on this project. It looks to me like my climate risk might be perfectly manageable, and maybe I should worry about other kinds of risks. So let me switch to some other kinds of risks in a moment. The vulnerability assessment approach. Here's a story from Nepal that's about those other climate risks. Those other risks, not climate. There's lots of uncertainties in this story from Nepal, and maybe the climate change uncertainties aren't the most important ones. Okay. There is a hydropower project that has not yet been built. Let's see, it's right here. It's called the Upper Arun Hydropower Project. This is the border. So for those of you, to get you oriented, here's China, here, Chinese Tibet. Here's Mount Everest, like right here. Here's Nepal, really sheer down, and then Kathmandu's over here somewhere, over here, I think, can't remember. And then down here, this goes down to the Ganges River and out to India and out to Bangladesh. This is the border, which is a sheer mountain border between Nepal and Tibet. 98% of the watershed is in Chinese Tibet. China doesn't play with the World Bank. This is a World Bank project. So the World Bank can't say anything to China about what it's hoping they're going to do. So China's going to do whatever China wants to do in Chinese Tibet. Are the uncertainties percolating for you? So when we analyze these things, we think, well, how much of this is China just going to divert away? It's totally possible and totally within their rights. Their land, it's their sovereign place. The World Bank doesn't have jurisdiction there. So uncertainty number one, what's China going to do given that they have 98% of the watershed? Fascinating, right? Okay. Here is the way we analyze this, and this is a challenging figure. So forgive me, but I'm going to push right through. Here we had a three-dimensional plot before. Precipitation, temperature, and then the metric in the middle, right? Now we've got like a 7-dimensional plot. Precipitation, here's your precipitation. That was the y-axis before. That was the x-axis before. Change in temperature. And then we have all these other factors. Economic lifetime, like, is an earthquake going to knock this thing out, or is it going to live for a long time? Up high is a long economic life. This thing lives for a long time, and down here is it falls down early. Plant load factor is a measure of sediment, how much sediment's coming down and damaging the turbines. Capital expenditures, the selling price of the electricity, the discount rate, meaning the terms of the loan from the World Bank, and then here is the net present value of the investment. And when I select all of the climate change possibilities, so I've selected all the changes in precipitation, all the changes in temperature, and I've put everything else at its default values, its baseline values, I get a range of uncertainty about like this. Here's 0 net present value. Here's $1 billion of net present value. Here's about $300 million to about $800 million of net present value. What this is saying is when we run our scenarios through this modeling chain, and we run all the climate change scenarios, the biggest one we get is about $800 million of net present value. And the worst one we get is $300 million of net present value. So this is an example of a climate robust investment. There is no climate change possibility that we explored that would result in a negative net present value. So that's a pretty good investment. Then we start looking at other uncertainties. So here's economic life uncertainty. What if the thing lives longer or doesn't live as long? What if an earthquake happens and knocks it down? Then you get a wider uncertainty band. Okay, here's a wider uncertainty band, but still all above 0, not that interesting. What if you have a much higher capital cost than you expected? Because in Nepal, famously, they have capital cost overruns of 100% or 200%. What if the capital cost is higher than you think? Then your uncertainty starts getting big, right? You start seeing, oh man, I think my biggest uncertainty here isn't climate change. It's more like the investment cost of the project. And then what if you have the ability to sell this for a much higher price because China all of a sudden says, yeah, well, actually, we don't want to build our own hydropower project. We want to purchase your hydropower. That's exciting and totally possible, something that's being negotiated all the time. India, China buying the hydropower from Nepal. Well, if you could sell for a higher price, then all of a sudden you're talking about $4 billion of net present value. So you start seeing where the uncertainty is in this project that impacts the decision. It's not so much climate change in this case, it's other uncertainties. Okay. Then, and I'll go through this quickly, all of these things could be long discussions in and of themselves. Here's that upper Arun I was just telling you about. It's in a network of other investments. It's a river network, right? Here's Tibet up here. I keep doing that. Here's Tibet up here. Here's India down here. Well, there's all of these different investments that could be chosen by the World Bank. It's not just like the upper Arun is the only thing they could invest in. There's Arun 3, there's Dud Koshi, there's Sun Koshi, there's Upper Tamar Koshi. There's all kinds of choices. What should they invest in? What's the risk portfolio? And then you start getting into bigger risk portfolios, more parallel coordinates plots, optimization algorithms to sort through the portfolio. And you might end up deciding that you want to do something like, of those, my gosh, I keep hitting that button. Of those 6 or something hydropower projects that we were talking about, the one that looks the best is the Dud Koshi, the Upper Arun, and the Arun 3, and not those other 2 or 3. And you say, well, this is all about trade-offs, but these are the ones we think give us the best net present value, the best flood performance, and maybe the least possible, the least maximum regret that we could experience. Okay. Summarizing the role of decision science and all of this stuff, the future is deeply uncertain, and we have to accommodate it in our designs. Climate change might not be the most important uncertainty. So first, we need to identify how serious is climate change. Maybe it's not that serious. Okay, pay attention to the other stuff too. Vulnerability assessment helps. Likelihoods are secondary. We don't need to start with which climate change is most likely. Talk about that at the end. Do the vulnerability assessment, talk about likelihoods at the end. There's not a right answer, and there's different portfolios of investments that are possible, and it comes down to what your risk, what do you call it? Your risk tolerance is in different categories of things, like flood risk or net present value risk. Okay. All right, switching our story. This thing keeps turning itself off, which is troubling. Okay, switching our story to the value of infrastructure to the Ohio River. We're sort of transitioning from decision science for a minute to now we're applying our decision science to the value of our infrastructure in America. Why is Congress underfunding our infrastructure? Maybe just because they're monsters, because they're terrible, awful people, or maybe they just don't understand. I had my mind blown. One of the reasons I love this job so much is I'm constantly having my mind just blown. I can't believe the size of the opportunities. I hope that every person in this room walks away feeling like, wow, the bar is low. The bar is low. I think I can actually make a contribution here because people are not thinking this through very well. Here's an example. The US Army Corps of Engineers oversees almost all of the water infrastructure in America east of the Rocky Mountains and a lot of it west of the Rocky Mountains. We're talking about tens of thousands of dams. They have to write a report to Congress every year that justifies their budget. So every year they report to Congress mostly on their flood risks avoided. So they'll say something like, because of all of our dams and levees, floodways, 38 people didn't die. And here's the value of 38 lives, or something awful like that, right? They'll say, this is the value we offer to society. They're counting up damages avoided, lives not lost, this kind of thing. There's all kinds of benefits that's offered. This is an Army Corps image. There's all kinds of benefits offered by the US Army Corps to America. The net benefit calculations for the National Economic Development account of the US Army Corps of Engineers for America. Navigation, hydropower, flood's one of them, and all these other things. But they're only reporting to Congress, really, about their flood value. So we have a project with the US Army Corps of Engineers in the Ohio River to help them communicate to Congress the value in other categories. And we're focusing for now on the low flow. Most of the infrastructure in the Mississippi River was built for navigation. Let me say confidently, the Ohio River. I think it's true in the whole Mississippi, but you can correct me on that. At least it's true on the Ohio River that all this stuff was built for navigation. These other benefits became interesting only later on, like in the 1900s. But in the beginning, it was all about getting the ships up and down the Ohio River. They're not good at communicating and understanding what the value is in all these other categories. One of the reasons why they're not good at that, and here's another mind blow for us, is when we installed our gauges, what is our ability to actually even count the impact of the infrastructure on the river? This purple line is, we call it fish barriers or dams, right? This is when we were building our fish barriers, our dams along America's rivers, in this purple line. And there was a big boon in the construction. This is not just the Ohio River, this is the whole country. There's a big boon in the construction of these things from about 1920 to 1970. It was 50 years. We were building like crazy, all these dams all over America. The USGS was monitoring those rivers also at the same time, but slower. They weren't keeping up, right? Look at this. That purple line's outpacing the green line. The green line's trying to keep up. The green line's kind of going up steadily. The USGS is adding stream flow gauges. The consequence of this is that the very modern, like year 2020, 2023, interest in natural flow regimes, functional flow analysis, this kind of stuff that we want to do. We want to build policies based upon natural flow regimes. We can't do it because we actually put the stream gauge in after we put the dam in. We never measured what the flow was in this river without the dam there. So all we know is what the flow is with the dam there. So how do we make policies based upon natural conditions when we never measure the natural conditions in the first place? Big challenge. And this is the challenge that the Army Corps has in reporting to Congress their impact on the river. How have they changed the river? I don't know. We didn't measure what it was before we put the dams in there. Oh, shoot. Darn it. Okay, so we have to try to solve that. Here's a picture of the, yeah, you may not be familiar with the Ohio River. Let me not take that for granted. Here's the Ohio River. Here's the Mississippi coming down like this. Smithland is approximately where the Ohio River dumps into the Mississippi. Here's Pittsburgh up here, yeah. And here's the Ohio River coming down. Here's Ohio and Illinois and Indiana, Kentucky, and Cincinnati is here. There's all these spots along the Ohio River where we want to understand what is the Army Corps doing to the natural conditions. What's the value? Before we get into questions of what the value is for hydropower or navigation or whatever, we have to just even count what's the difference in buckets of water. These bar plots are, again, focusing just on low flow, on the dry season every year. So the wet season is the winter and the spring, and then the dry season is the late summer into the fall. So we're saying the dry season is June to November, where it's actually very dry right now in the Ohio River. It's super dry. It gets most dry in about September, October. So we're saying in the typical dry season, half the year, June to November, how many days is the US Army Corps of Engineers providing 25% at least of the water? Some of these are just arbitrary numbers we're playing with, right? We can visualize this in lots of different ways. But in the dry season, 6 months, there's 180 days, yeah? So if there's 180 days, let's say up here in the upper part of the Ohio River, like 90 to 100 days, at least 25% of the flow is coming from the US Army Corps of Engineers. So the Army Corps of Engineers can at least say to Congress, if you let our infrastructure fail, if you underfund it, if you don't value it, you're going to be down at least like 25% in the river in a typical dry season. And you may have, this is Smithland here, we're focusing on Smithland's the most important one because it's right before it dumps into the Mississippi River. Here's a picture of when the augmentation is happening. This is January going around in a circle to December. And you see in a typical year, this blue, you are actually pulling water out of the river, or you're catching it, you're holding flow back. And then in the dry season, you're adding more water to the river. And in some years, some like special years, you're adding as much as like 35 or 40%. of the river, you're providing 35 to 40% of the flow in the river. So this is huge value to America that allows us to do things like ship passage and everything else. So we're trying to count that. This is a new result. We haven't even published it yet. We're just finding it now. Okay. One of the reasons why this is so important is something called 7Q10. Have people heard of 7Q10? A little bit. 7Q10 is the 7-day rolling mean, the week. 7-day rolling mean, lowest value that minimum 7-day rolling mean that occurs once every 10 years. Okay. So this is, you're saying, like, you know what a 10-year flood is, right? Your biggest flood every 10 years. This is your 10-year drought. This is the lowest the river gets and stays low for 7 days every 10 years. And our regulations about how much wastewater you can put in the river is based upon this variable. So the National Pollution Elimination Discharge Standard of the EPA that dictates how much wastewater we can put in a receiving body, whether it's an estuary or a river or whatever it is based upon this number. And our infrastructure has changed that value from here, the old naturalized flow. This is, again, what we just calculated. We had no way of knowing this before 3 months ago. The old value is here, and look, the minimum flow in the river is all the way up there. So that means that we are allowed now to put much more wastewater into the river than we would be if that Army Corps infrastructure weren't there. Does that make some sense? In a typical October day, without the Army Corps infrastructure, Pittsburgh might not be allowed to flush. They might not be allowed to put their wastewater in the river because so much of the water is coming from the Army Corps infrastructure that we now rely on that water being there so that Pittsburgh can continue to function as usual. So at the next step of this project, decision science, we're going to try to translate some of these insights into economic terms. And that means what are the ramifications of these findings for water supply? What are the ramifications for sewerage assimilation, which is something I just told you a little bit about, with Pittsburgh being able to flush because the river is big enough that it can receive the wastewater. And navigation, of course. So we need to count like how many ships would not be able to make it up the river if the Army Corps were not releasing this water. Yes, other benefits. Okay. One more story. Let's do one more story. So we started with decision science and went to focus on value and how would we think about the value of our infrastructure? How has it changed natural conditions? How does it enable our lives? And the bigger picture is some reflections on needed next steps for water systems planning and management, but also a story for what I'm hoping to do with the University of Minnesota. Here are the sort of 3 pillars, I guess. Pillars is that's a big word. I like that. Pillars. I think I just made that up. Okay. 3 pillars, 3 legs of the stool. Decision relevance. It's very important to me that as an academic, what I'm doing is decision relevant. We need to gather all the data that we can. This is a moment in time of big data availability. I'll show you an experiment we're doing on big data in a moment. Let's take full advantage because decisions are important and making the wrong decisions has deep consequences. So let's do our best. Let's make sure we have skills in all these things. Let's make sure we know how to access the satellites and do machine learning and uncertainty analysis and all the sort of thing that we need to be able to do. That's just essential. It's just what we have to be able to do to make good decisions. And let's design our models and design our experiments in such a way that they are calibrated toward equity. So in the case of the Ohio River, for example, make sure that you're not just taking care of Pittsburgh and you're not just taking care of Cincinnati. Take care of those small towns in between. You can do that if you design your experiment to do that. Okay, a story about South Africa that turns into a story about Minnesota. All right. Every one of these stories I have to go through so much faster than I want, but it's a good story. I'll tell it quickly. Working with the United Nations, UNESCO. UNESCO, anybody know what UNESCO stands for? E. Oh, close. This is really important, guys. We're in a university. What's the E for? Education. Yes. Okay, so you know what's really exciting? Jill Biden brought us back into UNESCO. We've been out for a long time. We've been back in UNESCO for 1 month. 2 months, July 25th, she brought us back and we were out. We're like, we're not into that. Education, tap out. We've been out of the UNESCO for a while. We just rejoined, so this is very exciting. We are, America's in UNESCO, guys. Isn't this great? Educational, scientific, and cultural organization. I say economic every time. Keep beating it into my head. Okay, of course economic also. Educational, scientific, and cultural organization, what they do is primarily they look after World Heritage sites all over the world, and they try to make sure people understand how to care for the earth. They look after the Millennium Development Goals, like make sure that everybody gets a good education, make sure that everybody has access to water and sanitation. They do a lot of gender equity stuff, so pretty cool organization. So, biosphere reserves throughout South Africa. Here's Cape Town. Here's Kruger National Park. Kruger National Park up here. It's a wide range of environmental factors throughout this country. Lots of things going on. Here's some pictures. It will help you if you see pictures. Anybody hear of the day zero drought recently, maybe 7-8 years ago? Cape Town essentially ran out of water. There were months, there were weeks away from shutting off the water to all of Cape Town. People were leaving en masse from Cape Town. Pretty serious. So in part because of that day zero drought, 2017, 2018, UNESCO went in and they said, oh man, we need to look after the water resources here. And it seems to be changing. Climate change is affecting it. I was there recently as part of this trip. Let me show you a few pictures of what we're talking about. Blythe River Basin in the northwest, northeast. Lions, tigers, zebras, elephants. This is what UNESCO is trying to do. It's trying to look after these. The penguins are in Cape Town, the biosphere reserves. This is a World Heritage Site. We want these animals and these bio systems, to be there for our kids and our grandkids. So UNESCO wants to make sure that this heritage is available to future generations. They're suffering from droughts. They're suffering from increased temperatures. And so UNESCO wants us to do a vulnerability assessment on the animal parks, really. Okay, so I showed you this a little bit before, this workflow of models, the weather generator, the hydrologic model, the multiple scenarios. The JAMS is a particular hydrologic model in this case. We run this system of models many times. So the hydrologic model and the impact model are models of animal reserves and biospheres. Here's the techie part of this I'll tell you about. Here's South Africa. What I'm showing you here are pressure clusters. So what we're trying to understand is what is happening to the climate. And this is big data. So there's something called NCEP reanalysis data. It's from NCAR, the National Center for Atmospheric Research. And they have data sets of historical climate. It's basically exactly the same stuff as the general circulation models, but run over the past instead of the future. So you can get at these grid cells, this is boxy, right? Little grids. You can get data at these grid cells for the whole world, download it right down to your computer, for what has happened in precipitation, temperature, relative humidity, pressure, wind, whatever you want, for about the last, well, this one's only since 1979, but since 1979 for this one to the present time. And we can get a story every single day. It's actually like every 3 hours, I think, over that time frame for what the pressure has been and the wind and everything else all around South Africa that have resulted in rain. We're trying to understand how is the climate changing and how is that affecting the precipitation and temperature in South Africa. When we model the pressure zones and we see how they change throughout the year, and I'm going to skip forward a little bit because I know I'm running out of time, we see how they correlate to precipitation. So we see that certain pressure clusters are associated with a lot of precipitation in certain parts of South Africa, and other pressure regimes are associated with dryness in other parts of South Africa. So the same ones that are associated with, these ones have a lot of rain in the northeast and no rain in Cape Town. And so we're trying to understand what's happening with the climate and the pressure regimes around South Africa. And what we see, amazingly, is in the last 10 or 20 years, they're changing like crazy. The weather behavior around South Africa is changing like crazy. And we're getting way more of the certain weather regimes that result in drought in South Africa. We can look at this with the general circulation models as well. The solution to this, and this is me wrapping up here about how this story becomes a story of Minnesota. The idea that the United Nations has, that UNESCO has to solve this problem, the pressures are clearly changing, and that results in jet streams that result in different precipitation throughout South Africa. As that's changing, we're observing, it's not future, it's historical, it's happening right now. We're seeing it happen. The idea is, well, build these things called nature-based solutions. Invest in artificial wetlands and floodplains and things that will help us to catch the floods and hold the moisture better so we have less droughts. This is a huge amount of enthusiasm in the world about these things called nature-based solutions, which we think we can build to combat floods and droughts. There's been some really cutting analyses lately in the last 3 or 4 years, saying that, though I'm talking about trillions of dollars of investment, right? From the European Union, from the United States, the executive order of President Biden, just was it last year or 2 years ago, that said that, you've heard about these trillions of dollars in America's infrastructure that we want to invest. So the Biden administration and Department of Transportation and everybody else, FEMA, is saying, well, as we're investing in America's infrastructure for climate change, and the Europeans are doing this, the UN is doing this, the World Bank is doing this, we don't want to just build concrete and stone. We want to build nature-based solutions. We want to build out of dirt and plants and things to use the benefits of nature. We have all this enthusiasm and billions of dollars to do it, but we haven't rigorously assessed the ability of this type of infrastructure to actually solve the problem the way we know that concrete and stone can solve the problem. So if you have a water-related problem, like, for example, the flooding in Boston, and you're trying to make a plan to solve the flooding in Boston, and you know that you could build a stone seawall to solve the problem in Boston, you would get your performance data on all the other seawalls that have been built around everywhere else that's like Boston, and you'd have your design guidance from all of those other stone seawalls, and you'd have a great infrastructure plan, a design. Now, if you wanted to go green, and you wanted to design a nature-based solution, you would find that you have a lack of performance data. And if you have a lack of performance data, you're also going to have a lack of design guidance. And you're not going to be able to get to a nature-based solution infrastructure plan. So you're going to end up right back here in gray infrastructure. This is the problem I think we're facing with all of the enthusiasm about green infrastructure. If you have a very serious problem, you're going to need a serious design guide to get yourself to a solution. So what we're doing here with the University of Minnesota and many others, here's a proposal we just submitted to the National Science Foundation last month with a large team. This is the Army Corps of Engineers and UNESCO and other universities, the Nature Conservancy, Deltaris in the Netherlands. We're going to try to figure this out. We're going to try to survey a large sample using machine learning, big data, clustering analysis, and figure out what the performance of these types of nature-based solutions are around the world so that we can actually create the kind of design guidance that would help engineers fulfill the hopes and dreams of the politicians who have identified nature-based solutions as the path forward. Skip this slide. Minnesota is going to have important roles in water chemistry and geomorphology at SAFL. Okay. We need to design for a deeply uncertain world. Maybe, this is risky of me to say, statistics are more important than calculus for this. We need to accommodate a diversity of values. Big data, machine learning, multi-objective optimization, trade-off analysis allow us to do this. And at the next phase, We want to get better at understanding the connections between the climate and the ground. We want to get better at understanding the likelihoods of different kinds of changes, improved credibility of our nature-based solutions models, and an understanding of the multidimensional interactions on complex variables such as river water quality that we really haven't talked about today, but it comes next after you begin to understand water quantity. Okay, so hopefully I made it in some good time. Thank you.
All right, thank you so much. So first I want to present a CG mug to you for coming.
Thank you, I love it. Makes me really happy.
And I'm gonna actually be a little radical since we have a reception right after this. And so everyone in the room will hopefully be able to join us at the reception and chat up Patrick and ask all of your questions. I'm gonna see if there are any questions on Zoom, and we can cover those first. Are there a couple questions? Not yet? Okay, does anyone in the room have a question? I knew you would have a question, Randall. All right, I'm gonna try to keep it to about 3 questions total, and I'm gonna keep checking in on Zoom, so.
What evidence do you have that politicians are capable of incorporating probability and statistics into the decision making? I have looked for it and have yet to find it.
I love that question. That's a great question, and it's a real life. We have a project right now with the Millennium Challenge Corporation, which is a wing of the US federal government that is for international development. It's meant to accomplish the Millennium Development Goals. It's a big fund, basically. The way they have made their decisions for the past 20 or so years is based on one number. So exactly what you're saying, something called the economic rate of return. You calculate a single number, and maybe you put a tiny bit of uncertainty bound on that, but not a probabilistic, you just a range. The title of our project is Cost Benefit Analysis Under Uncertainty for the Millennium Challenge Corporation, and it's really tricky. It's really hard. Yeah, they're not fond of probability distributions on that economic rate of return. They want one number. They want to know, are we going to make 5% on this? Are we going to make 12% on this? So yeah, I think it's a very real problem, but I guess I would say it's worth a life mission to try to break through that barrier. Thank you. Thank you. It's a worthwhile way to spend one's life, I think. Yeah.
Kella, is there a question online? Nothing yet? Okay, great. I'm going to go over there and then I'll come back over here.
You showed a graph about the delta T and the delta P.
Yeah, back in the beginning,
with
maybe.
Red zone and a lot of dots. I mean, blue zone, right?
Yes.
And then you have like a group. What is a design or targeted risk you design the structures for?
Sorry, can you repeat that? What's the design?
It's a design risk, because when you design it, right, this picture.
Yep.
Right, you have this uncertain domain, and then you have a part of it protrude to the red.
What's the color represent?
No,
saying?
What is the risk, the actual risk, the probability you want this blue zone cover the red part? Because you design a system, you design against the probability. What is the actual risk you are going to design the system for?
Let me try to answer. Feel free to correct my answer. Deterministically, so forget risk and probabilities for a second. Deterministically, if we run our model and we say this combination of precipitation and temperature, we get some performance. Let's call it hydropower. We make enough hydropower that we say we justify the investment and we're positive net present value. So there's no uncertainty, there's no risk idea there. There's just this combination of precipitation and temperature gives us this value. This combination is bad, gives us not enough hydropower, something like that. So that has no likelihood on it. There is no likelihood, so no risk, no probability. It's just a deterministic combination of variables. Then at the last step, we superimpose the probability question. We've already run all our models. It's confusing, it's layered. we've already run all our models. We're done running our models. And all we do is slap onto the picture, superimpose onto the picture, the uncertainty domain, the scatter from the general circulation model. Does that make a little bit of sense? So we're not running any of this stuff through our models. We're just laying it on top to see what combinations of precipitation and temperature the GCMs we didn't run these things, right? We just grabbed them from the Intergovernmental Panel on Climate Change. And we're just taking these dots and putting them on top of our model output. Does that make a bit of sense?
Yeah, but just say if I design the system, can I change the boundary between the red zone and the blue zone?
Yes, and that's one of the best things about this way of doing it. The boundary between the red and the blue is your threshold. It's a stakeholder-informed threshold. The threshold might be 0 net present value. So you say, I am perfectly happy designing and building this thing if I get a net present value of $1, positive dollar, then great, I'm in the blue. But you might say, I'm not building this thing for a net present value of $1. I'm going to build it for a net present value of $100 million, and I'm going to build it. So this threshold, we have these stakeholder meetings in Nepal or in wherever we're having these stakeholder meetings. And we talk a lot about that threshold, and we move it around. And we run lots of different experiments with different thresholds. So this red zone totally shifts around and the blue zone shifts around. And things make the red zone shift around, like demographic projections. What do we think is going to be the electricity demand in the future? So lots of moving parts here.
Okay, thanks.
Thank you.
Okay, one question from the audience is particularly relevant to the last part of your talk. So do you think there is enough data on the performance of green infrastructure or nature-based solution out there? If not, what we can do?
That is if not, what can we do? Yeah, exactly. I guess I'm saying I hope there is. I hope there's enough data. It's a lot of clicking to get there. Okay. The US Army Corps of Engineers has a program called Engineering with Nature. And they oversee, it's got to be at least hundreds, if not thousands, of pilot demonstration places where they're playing with dunes and seawalls and estuary modifications and floodplains and river meanders, all kinds of things the Army Corps is doing. The University of Iowa has a huge program in this. The University of California, on and on. There's the University of Maryland. These are our partners on the proposal, right? I think this is the big data mining, clustering thing that we're hoping to do with this project. I'm hoping if we get together everybody in the world that has these things, by my count in the proposal we just submitted, I counted that we would have at least 2,000 to 3,000 locations where we have some data, where there's an institution, a university or an agency running these things, instrumenting them, measuring them, seeing how they perform over at least the last 5 years. So I'm hoping that 2,000 to 3,000 data points, 5 years, gives us enough of a snapshot of what's happening in terms of, we're most interested in flood and drought management. So how much can get infiltrated, how much is being evaporated, and the geomorphology, how fast is it changing the dynamics? So yeah, I have to believe that there's enough data to do this, and I'm gonna try to gather it from all the people in the world that have it. Yeah.
Thank you.
Right, I think I'm going to actually close it because we're about 7 minutes over, and we've got a reception right afterwards. So you can come on out here, and there's beverages and food, and I hope that you all stay for a little bit and visit and talk to Patrick some more. So please join me in thanking Patrick. All right, thank you.